Okay, good. All right, so what we're going to do today is we're going to talk about the multilinear regression model. I usually use my Apple Pen, as you know, but for some reason I charged it overnight and it was not charged. So I'm using another pen, which I hate, but I will try my best. Okay. So a multilinear regression model is the expansion of a single regression model. A single regression model is a model in which I have, is a model in which, in which I have y is a function of x, but it has a certain intercept that we all the time are going to call it beta naught plus a partial slope beta 1 x. And because this model moves over different observations from the first person all the way to or person number n or student number n, and suppose I'm kind of analyzing, for example, this is let's see any example. Okay, so suppose that I'm analyzing how the test score is affected by the class size, and I think that the class size has a negative impact on the test score, such that as the class gets bigger and bigger, the test or the average test score falls. Okay, so I have to have a subnotation I under each variable here. Okay, and I also need to have something that can capture all mistakes or all possible mistakes, and we call it UI, the error term. So this one is called the Regressor, and I know that you know that this is called the dependent variable from your math course, and this is the X is called the regressor. So we have the regressor or the independent variable, as you used to call it in your math course, and this is your intercept, and this is your partial slope. And we know that beta 1 is measuring how yi changes because of the change in xi. Okay, and the ui is all the mistakes, or we call it the error term, and in your textbook they call it the residual term. I'm sorry, my pen is not smooth. Okay, so residual term or error term. Okay, and it basically captures all the mistakes that we have done, anything that we have not included in the model, and so on. So this is what we have here. Like what you see here is, this is a very simple one regressor model, right? I have just one X, so it's one regressor model, or we call it single regression model. Okay, single regression model. And then when I talk about a multi-regression model or a multilinear regression model, is actually the expansion of that. So I have to include more than one X or more than one variable. So it would be like let me write with a different color because I hit the green with the red. It's not okay. Oh, sorry. Okay, so yi is equal to beta naught plus beta 1 x1 plus beta 2 x2, and we can actually make it more general and keep going up to beta k xk, okay, plus the error term. And I also have I everywhere, right? Sub I everywhere, I. And the idea here is this model is trying to see how x1, x2, x3, x4, all the way up to xk are able to predict the changes in the dependent variable or y. And I do have different partial slopes. I have slope number 1, partial slope number 2, partial slope number 3, 4, 5, all the way up to partial slope number k. So k here is equal to the number of x's or the number of regressors in the model. Okay, and the total number of coefficients or parameters, so we call the betas, we call them coefficients, we call them parameters because these are actually constants. So the number of coefficients I have k coefficients related to or attached to the x's plus the intercept. So the number of total coefficients I have k plus 1, sorry, this is 1. I have k plus 1, the number of coefficients in the model. Okay, so I have a total number of k plus 1. Okay, k plus 1 coefficients in the model. I'm just going to write this nicely. So the total number of parameters are k plus 1. So k is the number of x's I have. So here I have k axis, but I still have also another constant or another coefficient, which is the beta naught. So we count it as 1. So k plus 1 number of coefficients in the model. All right. So the plan for today is planning to go over the following main points. So one, or the first point I'm planning to cover is, I gave an introduction. We want to find how can we find or estimate the coefficients, okay? So there must be a way that we can find the effect of y on of x on y, or x1 or x2 or x3. How can I find these estimations? And I need to talk about the assumptions of the model. And I also going to provide you with many examples. We're going also to see how can we estimate this in Stata, right? So if you have already watched my video, then this would be easy or relatively less challenging than if you have not watched my video. Okay, so let's start with this one. So when I try to find the coefficients, there are things that we know, which is, I know that yi, which is unknown, all what I know is it has a certain intercept, it has a certain slope attached to x1, and then I have other variables, and then it has beta k attached with xk, okay? And it has a certain error term that captures everything that I forgot in the model. I'm trying to find an estimate for this yi, because yi, like, let's say you go to the internet and you try to download the data set on GDP. So this is going to be your GDP, right? It's just coming from the internet, you download it, you have an Excel sheet, and you get just the data set. But you're actually interested in knowing how inflation affects GDP, how interest rate affects GDP, how unemployment affects GDP, how many other factors affect GDP. So you have to kind of try to break down this y into its components or into the factors that have a major impact on it. And you can probably forget about the minor effects, or you can leave the minor effects to be included inside the error term. So you're actually trying to find an estimate. So when I say estimate, I add the hat, and it's going to be like yi hat. I know in order to get this hat, it has to depend on beta hat naught plus beta hat 1 x1 I plus beta hat k x k I. right? And then when it's estimated, then I don't have the error term included here. So the error term is only attached to the equation, which is which is equation number 1. We call equation number 1 as the population regression line. Okay, so this is called the population, it's unknown. Okay, and then this one is the estimated population regression line. Okay, and of course you hope that the distance between my true value and my estimated value to be as small as possible, right? And we call this distance as the amount of error I have, or y ui had. So ui is the amount of error that you have in the model that is coming from the difference between the true and the estimated, okay? The true value and the estimated value of y. So, and that's the idea, you're trying to minimize it, the amount of errors that you have, or you can be actually more specific and you say, I want to minimize the sum from I equal to 1 all the way to n, which is the number of observations I have in the model, right? And I'm going to do the same thing on the other side. So I have to add the summation sign right here. So it's equal to the sum from I equal 1 to n of this gap. And because I might have sometimes my estimation is bigger than the y, and I might have the opposite, my estimation is lower than the y. So sometimes this gap can be positive or negative. So in order to avoid any negative sign, you can actually make your life easy. And let me just remove all the mess I have here, right? And then you can make your life easy and say, okay, I know that this gap can be positive or negative, then I would be better off having a squared difference. And we call this one, and this is very important, the sum of the squared residuals. Sum of squared residuals. And you have some textbooks, they actually call it sum of the squared errors. If you have any question, just type on the chat. So I keep checking the chat. If you have any question, I would stop. All right, so the idea is I want actually to perform a minimization problem on the sum of the squared mistakes. And I want to do that with respect to the parameters I have, beta naught, beta 1, all the way up to beta k. So I want to try to find what are the set of coefficients that make this gap as small as possible, okay? And this is the idea of least squares, or we call it the ordinary least squares, OLS. So we are trying to find the set of parameters that minimize the distance between the actual observation and the estimated observation, right? And this would require us to perform the first derivative of the function with respect to each and every coefficient that we have, okay? So let's start with the simple model, and then I'm going to walk you through how to find the coefficients. And so let's see. So I would like to, again, I'm going to be using the simple model, and then because the extended version of the model would require the use of metrics, and I'm not going to talk about metrics in this course. So I'm going to be using the one that I can perform by hand. And the idea is to let you understand how Stata is working, right? I'm not planning to ask you to derive this in an exam or anything. The exam is open book anyways, but this is just for your own learning to understand how Stata is working in the background. So again, I want to minimize the sum from I equal 1 to n of ui hat squared, which is equal to the sum of from I equal 1 to n of yi minus yi hat. I can open the yi hat to its components with beta hat node, right, minus beta hat 1 xi squared, right? And then you already know that this part is actually coming from yi hat. So yi hat has beta naught plus beta hat 1x, assuming that I just have a simple regression model. Okay, and then if I want to perform this minimization with respect to just the two coefficients I have, beta 1 and beta naught, then let's do the first one with respect to beta naught. So the derivative of this function with respect to beta naught is equal to the sum from I equal 1 to n of yi minus beta naught minus beta 1 x1, right? So I'm trying to get the derivative of this function, okay? Just let me remove this equal sign. So I'm trying to get the derivative of this function, which is equal to negative to the sum yi minus beta naught minus beta 1. And I have here an xi that I forgot, okay? And then I have here xi. And we can call this as equation 1. And then I can do the same, this is beta naught, right? And I can do the same with respect to beta 1. I'm trying to find the derivative of this function again. Okay, with respect to beta 1, but beta 1 has the multiplication with x1, so you would have to take the derivative of what is inside this function. So here I have I1 to n. Remember here also I equal 1 to n. All right, and then yi minus beta naught minus beta 1 x1 beta 1. Okay, and then xi. All right, and next, what I need to do is to solve for beta naught and solve for beta 1. So how can I solve for these? In order to solve for these functions, you basically need to set the derivative equal to 0. So to set the derivative equal to 0, so this is number 2, okay? So from 1, if I set the derivative, set 1 equal to 0, I can solve for the intercept of the function, right? So it's going to be minus 2, the sum from I equal 1 to n of yi beta naught minus beta 1 x, right, equal to 0. And negative 2 with 0 is just gone. Like any constant is equal to 0, then it's gone. The sum from I equal 1 to n of yi, I can replace this part by n y bar. Why? Because I know that, let me write this here. I know that y bar is equal to the sum of yi over n. It's the average, right? So I can always remove this one and type instead ny bar. So this is what we're doing here. Next, the summation is going to go inside with the beta naught. So the sum of something that is constant, right? The sum of something that is constant, it's basically going to be equal to n times this constant. So if I'm summing 5 plus 5 plus 5, I can say it's 3 times 5. So this is exactly what we're doing. So sum of something constant that is going to be repeated n times, then it's going to be equal to n beta naught, right? And then the last one, again, the sum of xi, it's going to be n beta 1 x bar is equal to 0. And the thing that I keep forgetting is the hats everywhere, right? So because this is an estimated model, so just make sure that you have the hats everywhere. Okay, so I have the hats because I'm talking about an estimated version of the model. Now I'm going to divide by n this equation. So if you divide by n, just to try to solve for beta naught, divide by n, and then solve for beta naught, you will find that beta hat naught is equal to, and this is very important, y bar minus beta hat 1 x bar. So this is our first important result. Our first important result is basically saying that if you give me a data set and you ask me to compute the intercept, let me go back and show you what we want to find in this simple regression model. So we're trying to get this one. So we are able now to get an equation for this beta naught by saying that beta naught is equal to the average of yi, right? It's equal to the average of yi minus beta 1, the average of x bar. But in order to be able to compute this, I can get the y bar from my data set. Like it's the average, the mean of y. If I have a data set on GDP and inflation, I can easily compute their averages. So y bar is the average of GDP, let's say. This is the average of inflation. So this is not a problem. But now I need actually to find or figure out what's the value of beta hat 1 in order to be able to get the value of beta hat naught. So that brings us to the next step, which is in order to be able to compute the beta hat 1, you actually need to solve for equation number 2. So you need to solve equation number 2, again, setting equation number 2 equal to 0, and then solving for beta 1, we can find the value of beta hat 1 in order to complete this. So okay, so let's take setting equation number 2, set equation 2 equal to 0 and solve for beta 1. So I need now to solve for beta 1 after setting this equation equal to 0. So if you go back here, I need to take this equation right here, set it equal to 0. So I'm going to repeat it just for convenience. So it's going to be minus 2 the sum of yi minus beta naught minus beta 1 xi equal to 0. And then again, a negative with the 0 is gone, right? So I need to take the summation operator inside. So it's the sum of yi xi. And then again, I have a summation that is going with I have an xi multiplied by beta naught, and I have a summation sign, so it's going to be equal to beta naught the sum of xi minus beta 1. I have xi, then it's going to be xi squared. The sum of xi squared is equal to 0. Again, everywhere hats, right? And then I need now, so let's call this one as equation number 3, and then let's do equation number 4. I know that, you know this already. If I want to find x bar, then it's equal to the sum of xi over n, okay? And the same thing for y bar x bar, it's the sum of yi xi over n. So I can do this here, right? So I can say, okay, this one is equal to ny bar x bar and beta naught nx bar minus beta hat 1 nx bar squared equal to 0, and this is going to be our equation number 4. Now what we're going to do is subtract 3 from 4, and just to try to simplify our model, okay? So when I try to get the 3 minus 4, then I'm having like the sum of yi xi minus n y bar x bar minus beta naught, the sum of xi. I'm sorry, my pen is like, it's not that smooth as I wish. I'm trying to charge my Apple Pen. It's just like, it's not charging. It needs to be charged overnight. So I hope, I'm just trying, I hope that works. Okay, and then plus beta naught n x bar. And then the last part was gonna be like beta 1, the sum of xi squared minus n x bar squared equal to 0. Okay, if I divide this equation by n, so if I divide by n and solve for beta hat 1. So if you divide by n, the one thing that I forgot to mention is these two are going to cancel out. I have nx bar here, which is equal to the sum of xi, beta naught and beta naught. So these two parts are already canceling out, and I have an equation that has y and x, right? X and beta 1. So I can easily solve for that, right? I can easily solve for beta 1. So when I do that, it's like it's going to be 1 over n, the sum of xi yi minus nx bar y bar, and it's going to be divided by 1 over n, the sum of xi squared minus nx bar squared. And actually these two can cancel with each other, and you can write it in a very like in an easier way. So you can say, okay, it's xi minus x bar yi minus y bar over the sum of xi minus x bar squared. And this is actually simply the covariance between xi and yi over the variance of x. So after all these derivations, we are able to get this important, this important formula, which is saying that beta 1 is simply equal to the covariance, right? It's equal to the covariance between y and x divided by the variance of x. And so that means if I have any data set, I can actually use it in order to be able to get the slope. And once I get the slope, I can plug it in here. Right? And multiply it times x bar, and then I have y bar from the data to get the intercept. And if I can do that, then I can actually be able to find the beta naught and the beta 1 of this relationship. In other words, I can get the estimated y. So to sum up what we have just said, and the good news is you don't have to, I'm just going to clean this red line so that you don't think I'm erasing it. So this is the sum of xi minus x bar squared. Okay, so we are able to get two important formulas. So to sum up, we have two important formulas. The intercept beta naught is equal to y bar minus beta hat 1 x bar, and then the beta hat 1 is equal to the covariance between xi yi over the variance of x. Okay, and this is very important, and it's kind of very easy to estimate whenever I have just a simple model in which I have just a single regressor, just a simple one factor that affects Y, right? In a multilinear regression model, I have more than one X. So it's not going to be that simple, right? It's going to be more of a matrix operation. So in the matrix operation, you would have like this huge matrix where you have all the X's included. And if you're going to pursue studies or advanced courses, any kind of metrics, everything is going to be like done in a matrix operation. It's not like just going to be like by hand. So in a matrix operation, you would have, I'm just going to give you like a brief idea just to understand how Stata works, because most of the models that we work with are multi-regression models. So in a multi-regression model, where I have more than one X, okay, and I have a set of observations where I start with Y1, let's say the first person I'm asking, or in a survey, for example, this is the second person I'm asking, and then the last person, let's call this person N. So I have N observations, and this one depends on a set of factors, right? And the set of factors are X1 for the first person, X2 for the first person, XK for, let me write this is XK for the first person, right? And then I have something here, which is the vector of coefficients. So this vector of coefficients is beta 0, beta 1, all the way up to beta k, such that when I multiply this times this, I get my equation. However, the beta naught need to be multiplied times something to get beta naught, so it has to be 1, right? So the first term in this matrix, we call this as the matrix of X, this is the matrix of Y, and the first one is a column of ones, so here 1, 1, 1 everywhere. And then the next one was going to be, okay, I need to have X, which is again the first X for the second person, the second X for the second person, and then keep going, XK2, okay? And then here I have X1N, and here I have X2N, and here I have XKN, right? And these all are multiplied with the vector of betas, and then each one, each person, each regression has its own error term. So I have an error term for the first individual, I have an error term for the second individual, and I have also error term for individual number N, or equation number N. So you can always think about this as the vector of Y's, this is the matrix of X, this is the vector of betas, and this is the vector of error term, okay? And in order to get our estimates of coefficients, it's just one notation, just like one formula, X prime X inverse X prime Y, and just note that these X's are not a variable. This is like I'm talking about this whole matrix, okay? So X multiplied times X inverse X prime Y, this would give you the same result as, so here X times Y would give you like similar idea of X times Y, and this is X times X would give you like the same idea as being the variance of X, okay? And this vector is going to be like a vector of estimates, so it would give you like the beta hat would be like beta hat naught all the way up to beta hat k, and we call this one as the vector of estimators or the betas, okay? So the good news is you don't have to estimate this by hand. You just give the command of regress to Stata, and Stata would estimate a model for you. So for example, you will be in Stata, let's say I have, a variable called test score, and I have how many students in class or students per teacher, and you want to estimate this model. So all what you need to type in Stata is a regress command. So you type regress st per teacher, okay? And it all depends on how the names of these variables are included in Stata, because you would have to type exactly the same name of the variables as you see it in Stata. All right, so before I proceed, I'm going to give you examples, okay? So I have actually many examples, and the examples are more interesting than these derivations, but the derivations are important because you actually need to know how Stata is working, right? You can't just like accept the numbers that you get from Stata without you knowing how these are computed. Okay. So let's take this example. Just give me a second. I'll go check if my pen is charged or not. 1 second. Okay. So I'm lucky. It's charged. Okay, good. All right, so let's take this example. I'm going to start with a single regression model. So this one here, suppose that I'm trying to estimate the factors affecting earnings, okay? And we call it earnings hat, so Y hat or earnings hat. And suppose that we are able to get estimates of this model by finding that this is equal to 23916 plus 5.20, and the factor I'm trying to study is age. Okay, so if you ask me how you got these numbers are just, we got it from Stata, and I'm going to show you how to estimate them, or you should have actually watched my videos. So I'm going to show you again. So this one refers to beta hat node, and this one beta hat 1, and already by looking at our important results here, the beta hat node is computed using this function, where now this one is going to be like earning bar, the average of earnings in the sample, and this one is going to be my age bar, or the mean of age in the sample. So once you have the mean of age and the mean of earning, you can just simply get the intercept, and if I have this information, I can get the slope, which is the 520. The information given is that I have a sample of people, N, of 1744 individuals, okay, and this earnings is measured per month. So this is a monthly data set. So the first question is, interpret the results. So you need to interpret the results of the model above, or the estimated model above. Okay, anytime I ask you to interpret the results, you actually need to move in order. So you look at the intercept and you try to evaluate the intercept. You look at the sign and you try to figure out, okay, what about this sign? You look at the partial slope and you try to figure out, okay, what does that mean? And so on. So you move in order 1, 2, and 3. So here, based on the results, what is the beta hat node implies? The beta hat node, which is equal to 239.16. The earning is in dollars, so this has to be in dollars, right? And it's monthly data set, so I said it's per month. And this one basically implies that at age 0, the estimated earnings or earnings hat is equal to $239.16 per month, right? And of course, like at age 0 doesn't make any sense, right? Because I don't have age 0. Like how if the person is age 0, then no earnings. But at many times the intercept does not have a meaningful economic sense, but it can only have a mathematical sense, like this case. It only has a mathematical sense. You still just write down that at age 0, because this is the definition of an intercept. An intercept is the value of the dependent variable at 0 independent variable, right? So here I have that at age 0, the amount of earnings is $239.16 dollars per month. What about the age? So I know that beta hat 1 is equal to 5.20. Age has a positive impact on earning as the person gets older, right? Because as age increases, earning also increases. As the person gets 1 year older, earning also increases, but it has to increase with a certain magnitude. So the magnitude of the increase is 5.20. So this one is saying that as age increase by 1 unit, and you can say unit here is year, right? The estimated earnings or earning hat increases by $5.20. So each additional year in the person's age increases the amount of estimated earnings by $5.20. Okay. On my video on the measures of fit, which is the R-square, have you watched that? Have you watched the video on the measures of fit? Type yes, no. So here the adjusted, the R-square of the model is equal to 0.05. The standard error of the regression, as you have seen it on my video, is 287.21. So how can I make sense of these two important statistics? So for the R-square, it's about the explanation of the model. So the R-square is telling me that age, right? No, sorry, it's not age. The regression model explains 5% of the variation in estimated earnings or in earnings hat. Okay, so there is only, this is very low, right? Because I want to maximize this as much as I can. So 5% explanation is just a very, very small number. All right. What about the standard error of the regression? The standard error of the regression, we don't have like a benchmark on whether we can say how high or low, but the standard error of the regression is actually made out of the errors that we have in the model. So I want to minimize this as much as I can. If I can get this number to 0, then that's perfect. But actually, I don't have a benchmark to say, or it's not measured in percentage to be able to say it's high or low. But one way to interpret the standard error of the regression is to look at how big or small it is versus the height of the regression or the intercept. So by looking here, I can see that the standard error of the regression is higher than the height or the intercept of the regression. And this would be an indication that I have so much amount of error in the model. Okay, so this is basically a way to interpret this standard error of the regression, right? Because I don't have inventory. I can say whether it's high or low. I hope it's equal to 0. It would never be equal to 0 because all the time I would have a certain amount of error in my estimation. But one way to try to make sense out of the relation is to compare it with the height of the relationship, which is the intercept of the model. Now, let's complete this example. So the first part was to interpret the result, right? So this is number A, number B. Like these are the type of questions that you would get with these models. So the question would be if the average age in the sample is 37.5 years. This is the average age or age bar. The question is, what is the average monthly earnings? Okay, so from here I know that age or the average age, which is age bar, or you can think of it as X bar, right? So I'm like giving you this equation. Let me go back here. So I'm like giving you the X bar and I'm asking you about the Y bar, and you have this information, you have this information. So you have everything given except the Y bar. You're asked to get the Y bar. So you can actually solve for it. So using this equation where I know that beta hat naught is equal to Y bar minus beta hat 1 X bar, or you can write it in terms of the notation of our model. I know that beta hat naught is equal to earning bar minus beta hat 1 age bar. This is given. I have this one and I have this one. I need to solve for earning. So yeah, so this one would be like earning bar is equal to 239.16 plus this is 5.29, and then I plug in the 37.5 here, I would get $434.16 per month. Okay, so the answer to the question is the average monthly earning is equal to $434.16 per month if the average age is 37.5. Is this clear? Can you type if you have any question? Is it clear? Yes, no? Any questions? Yeah, I can explain it one more time. Which one? You want point A or point B? Okay, point A. All right. So point A is all about interpreting the results. Have you watched a video on the measures of fit? Just type for me, yes or no. Okay. So, okay, good. So, the point A is actually asking you to interpret the results, right? So interpreting the results, as I said, you actually need to move in order, right? So you have to go into first the intercept. What does that mean? What the sign means, what the partial slope means. So the intercept, like when you analyze the intercept in any mathematical model, it's the value of the dependent variable at 0 independent variable. So 239.16 is the value of earnings hat, or the estimated earnings when age is equal to 0. And given that age is not equal to 0, we will just say it's a mathematical meaning rather than an economic meaning. Okay, so at age 0, earning hat is equal to $239.16 a month, right? And this is only has a mathematical meaning without any economic meaning because I don't have any age equal to 0. The positive means that age has a positive impact on earning. As age increases, earning increases, and it makes sense. We were expecting this result. The 520 is the partial slope. It's actually the change in earning because of the change in age. All right, so for each unit increase in age, the earning increases by $5.20. And this is just the definition of the slope. What about the standard error of the regression? So let me just make sure that you got what is a standard error of the regression. So the standard error of the regression is one of the measures of fit. Okay, so what is a measure of fit? We said that we have different measures of fit. We have the measures of fit. I have a complete video on that, and I want you to make sure to watch it. So I'm not going to repeat what are the measures of fit here, but I'm just going to stress on the point related to this question. So the measures of fit, we have the R-square, we have the adjusted R-square, we have the standard error of the regression, we have the root mean squared error, we have the F statistic. Okay, and I'm going to show you the video that I want you to let me see where it is. I'm going to show it to you because you have to watch it. This is okay, so let me share with you my desktop. Okay, so if you go to Sakai and under week 8, when we were talking about the simple regression, I have posted for you an OLS example. So this is very important. It complements today's lecture. And you have 2 videos on the measures of fit. As you can see here, I have a standard error of the regression. So you have here 20 minutes, around 22 minutes, and here around 13 minutes. I want you to watch these videos. The standard error of the regression is actually made out of the error, right? It's made out of the amount of the errors that you have. So I'm going to just stress on this point now, but I want you to go back and watch these 2 videos so that we don't have to repeat the information again. So on the one that is related to our question is the standard error of the regression. Okay, so the standard error of the regression, SER, is actually equal to the square root of the sum of the squared residuals over n minus k minus 1. What is this? This is the sum of the squared residuals or errors, whatever you like. This is the one that I mentioned at the beginning of today's class. So let me make sure where it is. SSR here. Sum of the squared residuals. It's the amount of errors. It's the distance between my true observation and my estimated observation, and it's squared. Sum of the squared residuals, SSR. So the SSR is actually all about errors. You want actually to minimize this as much as you can, right? And the SSR, if I try to get kind of its average, I divide by the sample. I do some adjustment of degrees of freedom by taking the number of x's out and 1 for the intercept. So this is the number of betas, and this is the beta 0, okay? And this is the sample size. So I want you to think about SSR is trying to divide the amount of sum of the squared errors divided by the sample size, adjusted for degrees of freedom. And of course, if I have a large sample size, then this part doesn't really matter. Like this adjustment doesn't really matter. And you're taking the square root of that. Okay, you can actually write the SER, the standard error of the regression, as the square root of the sum of the squared errors, whatever you like, over n minus k minus 1. And then when I have this information here in the question, I have that SER is equal to 28721. How can I make sense out of this? I can make only sense about this is I actually need the sum of the squared errors, the square root of the sum of the squared errors to be as small as possible. I want this number to be actually 0. I don't have it here 0, so I'm trying to figure out how bad is this number. So to determine how bad is this number, you can compare it with the height of the regression. When I say the height, it's the intercept. This is the height, right? It starts from here, it's positive, and it's going up with a slope 5.2. So this is 239, but this number, the amount of errors actually on average is way above the 239, okay? So this would give me an indication that the amount of errors in the model is relatively large. People usually go with the R-squared to as an easier method to determine the measure of fit, because the R-square is a number that is between 0 and 100%, right? Or you can think of it as in terms of a fraction. So you can think of it as from 0 to 1, or you can think of it in terms of percentages, 0% to 100%. So people usually go with the R-square because it's kind of easier to make sense in terms of percentages. You don't have to compare it with an intercept or anything. So again, I'm not going to cover these here because I have 2 videos on that. So I want you to make sure that you complement today's lecture with watching the videos of measures of fit and the example on OLS. Any question? Okay, so what I'm planning to do next is to give you another example. So I have another example, and this example is more of a multi-regression model. So this other example, it's about, again, test score. How the test score is affected by the class size, and you have an intercept of 698.9 minus 2.28 times the student per teachers in class. And this is a measure of the class size. Okay, so you're actually trying to figure out what's the impact of the class size on the test score. And it makes sense that usually on average, when the class size increases, the test score decreases. It's like the students are getting less and less attention from the teacher, because when the class gets bigger, you would expect that there is no enough time for a teacher to just make sure that each student got the information. So it's kind of a negatively related expected relationship. So when I get this model, and this is the way that you actually get the results. Let's say if I'm giving you a model, I would give you the output as you see it like that. I would give you how each coefficient is measured. So this one is the number of students per one teacher. And this one is a test score, a standardized test score in California. And this was for N, or a size of the number of districts in the state of California, and these were 558 districts. Okay, so this is the sample size. And then how can I analyze this result? Okay, so again, you move in order 1, 2, 3. So 1, this is the intercept of the model, and it's telling us that test score, I'm going to write it as TS just for convenience. Test score is equal to 698.9 points, okay, at 0 students per teacher in class. And again, this is one of the examples in which you have the intercept doesn't make any sense, because how come if I have 0 students per teacher in class, I still have a test score output? So again, this one has a mathematical sense, no economic sense, right? But just we analyze it. The negative sign implies that we have a negative relationship between student per teacher and the test score. As the student per teacher increases, the test score falls, and this is an expected result or an expected relationship. But to be more specific, the negative 2.28 implies that as the student teacher ratio increases by 1 unit, and the unit here is a student, right? As I have an additional student in class, so this is the unit of measurement for a student-teacher ratio. So as the student-teacher ratio increases by 1 unit or 1 student, this implies that the test score falls by 2.28 points. This is the test score, so it's kind of it's a score, right? So it's 2.28 points. Okay. So this is, again, up till now, it's similar to what we have done. So suppose now that you want to add another variable here. Okay, so you want to control for other factors that might be also affecting test score. So you want to move from a single regressor model to a multi-regression model. So in order to do that, so we have to think about what are other factors that might be affecting this model. And one of the other factors is called the English learners. Okay, so this is the number of students learning English. So how the increase in the number of students learning English is affecting the average test score per each district, right? It's the average between all the districts, I should say. So the regression now, and again, I'm giving you just the numbers or the results, but we are going to estimate this together using Stata. So for now, this is just, I'm giving you the numbers. Student-teacher ratio minus 0.65 EL. So now we have added the effect of English learners. The result is expected. I expect that the higher the number of students still learning English in class increases, the lower is the test score. So it's a negative relationship, right? And what is the magnitude of this relationship? For each additional increase in the number of students learning English, or for each additional student in class who is still learning English increases, then the test score falls by 0.65 points. So let me write it here. Test score falls by 0.65 points for each additional student still learning English. okay? So when you look at, and one of the important things to notice is every time I'm adding a variable or an additional variable to a model, like here I'm adding EL, I need to notice what happened to the previously included variables. So I need to compare, let's say, here the student-teacher ratio was negative 2.28. So it was negative 2.28. And let's call this one and the student-teacher ratio was negative 2.28. In model 2, I'm going to call this equation as model 2. In model 2, the student-teacher ratio actually dropped. Its impact has dropped by negative 1.10. It's very, very important every time you're adding a new variable to notice what happened to the already included variable. What we can see here is the impact of student per teacher ratio on test score has decreased, right? It has decreased between model 1 and 2. There is a drop, right? And this drop is about 50%. So it might be, it's not might, it is the case that whenever I see this huge change in a coefficient from this number to this number, then it might be the case, or it is the case, that it was kind of absorbing the negative impact of the variable that I actually forgot to include here, okay? However, if I included EL and I don't see any change, like let's say I have included EL and the number here stayed around 2.2, let's say, then I won't say that there is any connection, like I would say that there is no connection between English learners and student per teacher. What I see here is a change in the coefficient of student-teacher ratio, and this implies that it was absorbing, right? It was absorbing the impact of EL. So this conclusion actually is just an indication that a student per teacher ratio in model 1 was absorbing the negative impact of EL that was omitted from model 1. It was we forgot to include it, or we didn't include it. So once we have included it in model number 2, this impact has decreased. And actually, every time we're adding an additional variable, we need to keep watching what happens to these coefficients, right? We need to keep checking what happens to these coefficients. If I included EL and I don't see any change in the coefficient of student-teacher ratio, then that's fine. They are not connected. But if I see any change, then this is an indication that I actually might be in need of this variable, right? Because otherwise, this would be overestimated. It's in type the chat if it is clear. Okay, good. Okay, perfect. All right. I'm missing Mohammed. He's not typing. Are you there? Okay, Mohammed, thank you. All right, perfect. So the other thing I want to show you is, like, as a continuation of this example. Suppose that, or let me, did I say 1 and 2? Let me see. This is just an example. Okay, let me type this question related to this example. Okay. So if we reduce the number of students per teacher, or the student-teacher ratio, by 2 students, okay? So now suppose that I'm going to reduce the number of students in class by 2 students, okay? Compute the change in test score, okay? So what I need to do is, I want you to think about, again, let me write it here again so that just for convenience, because the previous slide is getting messy. So I said that we have a test score that is equal to 686 minus 1.1 student-teacher ratio minus 0.65 English learners. The question is about student-teacher ratio. Like, we didn't talk about EL, it's about this one. So it's like asking you, what is the change in test score? It's like getting the first derivative because of the change in student per teacher, right? So I know that if I do the first derivative of this equation, this is a constant, so it's not there. Then I need to use this one, so it's going to be negative 1.1. Okay, and that's it. So this is the derivative, okay? Or I can write it nicely. I prefer to write it in terms of deltas. So the change in the test score is equal to negative 1.10 change in student per teacher ratio. So if this change here, like I can write like this is the nicer way of writing it. So if the change is 1, so that I can read it this way, the test score would fall by 1.10 points if the student-teacher ratio falls by, increases, I should say, if I have an additional student in class. In other words, if I'm asking you if I have an additional student plus 1, so the test score would fall by, that's the answer, would fall by 1.10. Now the question is asking you about 2 students. Okay, so that would be, and then it's actually reducing. So this would be negative, right? This is negative. So this one would be negative 1.1, negative 2, and the answer would be 2.2. So the answer would be, if we reduce the student-teacher ratio by 2 students, test score increases by 2.2 points on average, because this is the average between all the districts I have in the sample. Okay, is this clear? Yes, no, type. I'm waiting for 3 yeses. Perfect, thank you. All right, so what else I have for you? I have another example, and I do also need to talk about the, I think that's it for the examples. I give you enough examples. The last thing I want to, let me go back to our first, to this slide. So we discussed how we find the coefficients, right? Which is the long derivations that I want you not to worry about it, just to understand how Stata works in the background. So all the derivations that we did at the beginning of today's class is just for your own learning. And we discussed examples. Then we are left with assumptions, and then I'm going to show you Stata. So before we discuss the assumptions, I'm going to give you like a break. Let's take a 10 minutes break, Okay, so now it's 1:57, so we will come back at 2:07. All right, so I'm going to pause the meeting and then we will resume back at 2:07. All right. right, everyone. Are you there? Okay. All right. So, so what we have left is talking about the assumptions of the OLS model. So let's so any model is based on certain assumptions. So we said that OLS, ordinary least squares, which is the model that we are, or the methodology that we're talking about in today's lecture, is based on certain assumptions. Okay, and these assumptions are very important so that we can estimate the model. And later on, when you take econometrics 2, we will drop these assumptions and we see how the model performs in reality. So these assumptions might not make 100% sense, but they are needed in order to estimate the model, like the model that we just talked about, which is, I mean, this one. In order to be able to estimate this model, I need to have like set certain assumptions. The number one assumption, which is very important, is that the expectation of the error term given x1, x2, xk is equal to 0. Okay, so this one is telling me that the conditional mean of the error term, when I say conditional, it's conditioned on certain values taken by x1, x2, x3, xk, is equal to 0. In other words, the error term is not related to the x's included in the model. In other words, given any value to x1, x2, x3, any value, like any age, any number of students in class, any value taken by the axis, it will not affect the mean distribution of the error term. The error term, or the mean distribution of the error term, will all the time be equal to 0. And this also follows that the covariance of the error term given xi is equal to 0. They do not covary together, right? The correlation also, which is computed from the covariance of xi and ui, is also equal to 0. In other words, any included regressor, any included x in the model is not related to any variable that I left out. So any included regressor, let's say, this is called an included regressor, right? An included variable, right? I might have other factors that I left out and they are included in the error term. The error term might include, let's say, the economic background of the student, let's say the family income, or whether the student is on the school lunch or something like that. This factor or these factors are not included. The expenditure of the state per student is not included, right? So this assumption is telling us that any factor that is included inside the error term is not connected with the x's in the model. They are totally disconnected, which is a very important assumption because actually it might not be true, right? The student-teacher ratio might be connected with how the amount of spending per student, or the amount that the state would spend per student, let's say, or whether the student is on school lunch or not, or the economic background in general might be also affecting the test or the average test score. So this is a big assumption, and it's very important assumption, and I would like in the coming topics, I would briefly talk about the violation of this assumption, but I will not like spend much time on it because this is a part of your econometrics level 2 or the second course in econometrics. The second assumption is again very important. It's telling us that xi and yi, and where xi could be like the age of the person number 1, and yi is the earning of person number 1, because I know that I goes from the first person all the way to person number n. So xi, yi, where I goes from the first person to the nth person, or from the first district to district number n, or the first country to country number n, and so on. Those are IID. What is IID? Independent, identically, or independently, identically distributed. What does that mean? Independent is an important assumption, and it basically says that if I pick the first individual, and let's call the first individual as Y1, and you give me some information about the second individual, it will not help me. It will be everything about the first individual. So the conditional probability of Y1 given Y2 is equal to everything about Y1. And this is called independence in probability. Independence in probability. People are independent from each other, and you can replace the Y with the X. If I know the age of the first person, given the age of the second person, no additional information will not help me, right? So it's totally disconnected from the age of the first person. If you give me the number of students per teacher in district number 1, and I know, or I have an information about the number of students per teacher in district number 2, it's equal to everything about district number 1. Okay, the other one, so this is all about independence. What about identical? Identical actually means that each and every person has the same probability of being chosen out of the population to be part of the sample. So identical is about the probability. So the probability that I pick the first individual is simply equal to the same probability of picking individual number 2, and it's equal to the same probability of picking individual number n. So identical means equal marginal probability. Equal marginal probabilities, okay? So I have a sample, and again, I have this big population. I pick out of this population sample, which is smaller, it's a subset, right? Each and every person inside this population has the same chance of being chosen here, right? So that's what we call, they are, you know, identical. The same probability, each and every one here has the same probability of being chosen into the sample, and this is what we call, they have equal marginal probabilities. So independence is about the conditional probability. The conditional probability of Y1 given Y2 is equal to everything about Y1. And you can actually make it more general, and let me just make it instead of 1 and 2 because I have multiple individuals. It's not only 1 and 2, so I can make it more general, and I say the conditional probability of Y, let me call it Ym, given Yn is equal to everything about Ym, okay? So you can just have any letters. You can have 1 and 2, 2 and 3, 2 and 1, 2 and 10, whatever. So each and every, it's going to apply to each and every observation I have. And the same goes here, right? So this is assumption number 2. It's very important to notice the following, that when I have cross-sectional data, so I have cross-sectional data. What is a cross-sectional data? For example, I have 10 students, okay? And the 10 students, I'm trying to analyze these 10 students, the score of the 10 students in one, let's say, day, which is the final exam day, okay? So I have one time period and multiple cross-sections. So this is called the cross-sectional study. So when I try to apply the IID in a cross-sectional study, it's easy because there is no reason to believe that there is a connection between student 1 and 2, between student 3 and 2, 2 and 1, 3 and 1, right? 3 and 10. There is no reason to believe there is a connection. Okay, assuming that these are randomly selected sample of 10 students, they are working independently on the exam. So there is no reason to believe that the score of student number 10 would depend on the score of student number 1, assuming they work independently. However, if I talk about time series, this is a data set, time series data set. And the example here would be, let's say, interest rate of the USA over time from, let's say, 1990 to 2018 or 19, whatever. Okay. This is like, it's not easy to apply the IID idea here, because interest rate set by the Fed in 2018 is definitely related to whatever happened in 2017. It could be also related to what happened 10 years before that, and so on. So the IID assumption is violated in time series. I'm going to write the STS in time series data sets or time series models. And this would bring a lot of challenges when I estimate time series model, because I have to deal with this type of violation, or we call it the serial correlation. Each observation is correlated with the previous one. So we will have a serial correlation. So this is just something to note about the IID assumption. Okay, or the difference between what happened when I talk about a time series model versus a cross-sectional model. Okay, so so far we have two important assumptions: the expectation of the error term given the set of x's is equal to 0, or the conditional mean, and this is very important, especially when it comes to the point that we are violating this assumption and we're trying to drop this assumption and see how the model performs. And number 2 is the IID assumption, and we said it is easily violated in time series models. It can be applied in cross-sectional model because I can get the group of cross-section to be independent from each other easily. The third assumption is large outliers. My handwriting, just my outliers are unlikely. What is large outliers? So if I have a data set like this, I have X affects Y, and suppose I have the set of observations like this, right? Kind of tightly together. And I do have, and we call this as like the set of observations we have. And what we're trying to do is to fit a certain line through this observation, okay? And this is what we are trying actually to do, right? This is what we call the estimated regression line. Suppose I have a certain observation right here, outside the range of observations. Suppose I have something here, again, outside the range of observations. Then this is called an outlier, right? And an outlier is simply a data set that is outside the range of observations I have. I can put this in an oval shape or this kind of shape, and I can say that anything that is outside here is considered an outlier. It's outside the range of data set. And of course, this would create a lot of trouble in our estimation if I have outliers in the data set, because as you can imagine, the distance between this dot and the estimation, this is an amount of error. I'm gonna call it U hat 1. And also the distance between this dot and my estimation is another amount of error, U hat 2. Okay. However, the ones inside here are just tiny errors, right? Tiny amount of errors that are assumed based on assumption number 1. If you go back here, they are assumed to be 0. Like if I go up the line, below the line, on average, the conditional mean of the error term is equal to 0. So outliers are those points that are outside the range of observations. It's very important to check our data set. You're given a data set, it's very important to check your Excel sheet. It's very important to graphically represent your data set to make sure that you don't have any outlier. If I do have an outlier in the data set, you have to study what is this about. So whether this is something related to a mistake in the data set that I can correct, or this is related to maybe the data set, like one example of the mistakes would be like the data set is in dollars and I decided to, and one of the cells is in cents. So it's like a number that is huge. It could be related to a government, that change in a government policy, let's say. If it is something meaningful, if it is something that I need to capture in my estimation, then we have ways to capture it. But if it is related to a mistake, then you have just to remove it, right? Delete. So you would be like, okay, I'm going to delete this outlier if it is related to a mistake. If I can probably correct, then that's great. If you cannot correct, then just delete it. If it is important, then include it, and we will find a way to include it. All right. The last assumption, and this is our last assumption, is no perfect multicollinearity. No perfect multicollinearity. So we assume that I don't have any collinearity between the x's included. So collinearity here refers to the x's in the model. So let me go back to one of the examples we have to explain this. So let me go back to this one. So collinearity is all about the x's, student-teacher ratio, English learners, right? So it has nothing to do with the y. So collinearity is all about the x's in the model. And this assumption assumes that these two variables are not perfectly collinear. What is perfectly collinear? They are not 100% correlated. So a perfect collinearity is related to x1, for example, and x2, their correlation equal 100%. Okay, and if this happens, we call it perfect. And the assumption is that I don't have this. No perfect multicollinearity. And the perfect multicollinearity, like this case happens if I repeat a variable twice. So let's say, and we just assume that we don't do this mistake, right? So suppose that I have earnings is equal to beta naught plus beta 1 age plus beta 2 education plus beta 3 age again, right? And I'm trying to estimate this model based on my estimation of these coefficients. As you can see, the mistake we did is repeating a variable twice. So if I repeat a variable twice, this is a mistake. And this mistake would lead to perfect multicollinearity because both are 100% correlated, right? It's the same variable. But the good news is in Stata, if you do this mistake, it would automatically drop this one, right? It's going to drop one of the two to let you know that you're repeating the variable twice, okay? So this is assumed that we're not going to do this mistake, like repeating a variable twice. Of course, there are other ways of perfect multicollinearity that I'm not going to discuss here. But as you can see, it's saying no perfect, but it allows for the imperfect, okay? So if I have an imperfect, any multicollinearity that is below 100, it's called imperfect. And an imperfect could be, let's say, in the example that we had, or actually the example that I just wrote. It could be that we can have a correlation between the age of the person and education, right? We expect this positive relationship, right? As you get older, the number of years of education would increase, of course, up to a certain level, let's say. So we expect there is a correlation. When I try to compute the correlation, and as you know, in Stata, we type correlate or CORR age and EDU. I'm sure that I will not get a zero correlation, right? I might get like probably 0.25, which is 25% correlation or something like that. So this is an imperfect and this is acceptable, right? This is not the part of the assumption. The assumption is all about that we don't need to see a correlation that is equal to 1, okay? Or 100% correlation. Okay, so those are basically the 4 important assumptions of OLS that, the 4 important assumptions of OLS that are very important. I'm going to kind of refer to them almost every topic starting from today, because they are connected with the remaining topics. And sometimes when I try to estimate a model, I run into certain problems. And when I run into certain problems, I go back to my assumptions and see if any of these assumptions were violated and accordingly creating econometric problems. Okay, clear? Any questions? Okay. So then you're saying no, you mean like you're not okay or you're fine? Any questions? Thank you, no questions, okay. That's clear. All right, so I'm going to share with you Stata, and I'm going to return back to my iPad. I'm just going to show you how to estimate. So when I try to estimate a model in Stata, okay, I just like open one. This is something not related to your class, another econometrics class. So let me just take this here. So suppose I have the census population survey data set, and the census population survey data set we had used it before. But suppose that now I want to estimate a model, right? I want to do a regression. So let's clear, and let's use the data set. And to remind you, let's describe it just to make sure that we are on the same page. So we have years, we have average hourly earnings, we have bachelor, we have dummy variable female, that takes 1 for female and 0 for male, and then we have the age. And let's summarize, just to remember. Okay, so we have 7,440 observations for age, and as you can see, this is a continuous variable, right, of the average hourly, I said age, okay, this is the average hourly earning, okay, it's per hour, so it starts from 2.13, like 2.14, around to 91.5 approximately, and then we have 2 dummy variables, and then we have the age. The lowest one is 25, and then the highest is 34. Okay, so anything that you see on here is already something that you know up to here. Let's take the regression. If I want to now estimate the impact of age, getting a bachelor degree, and a female. Okay, so let's start with the single regression model. So if I start with a single regression model, I just going to have like here, and this is going to be a single regression model. Single regression model, you would get this output. What you see here is constant. This is the beta node. Age, this is beta 1. So if I want to read this output, I'm going to say that for each additional age, or I should say for each additional year of age, average hourly earning increases by approximately by $0.512 an hour. So whenever you're trying to analyze the effect of one variable over the dependent variable, you have to make sure that you know the unit of measurement of the variables, right? So I know this one is age, a year, and I know this one is per hour, so that you would include this in your sentence when you try to analyze the impact. Also, at 0 age, earning per hour is equal to 4.63 approximately. Okay, what about the rest? This is the standard error, t-statistic, p-value, confidence interval. These are other statistics that are very important and are discussed in my videos that I asked you to watch. So I would like, I'm hoping that you have already watched this or know what is this, but I'm planning to go over it again. All right, so let's, now I just discussed the coefficients, and the next is what if I just have a multi-regression model. So a multi-regression model, you would get again the output of the whole set of the whole set of variables that you have. So how can I read this? Number one, I wanted to notice that when I included bachelor and female, what happened to the age coefficient? I don't see like a big change, which is good. And this would be like an indication that bachelor and female are not so highly correlated with age, which is again a good result. Also, how can I analyze bachelor? So bachelor is basically telling me that a person with a bachelor degree earning would increase by about $8.32 an hour. For a female, okay, so a female worker in the sample, the average hourly earning drops by $3.81 an hour. Again, this is my the comparison here is between male and female. So I would be asking you how much females earn as compared to males per hour. As you can see, females would earn less by $3.81 an hour. Okay, and then at 0, all other variables. Okay, at 0 age, at 0 bachelor, at 0 female, the average hourly earning is equal to about $1.87 an hour. Okay, So this is how to read the coefficients. We're just talking about the first column here. Whether the impact of these coefficients on average hourly earning is statistically meaningful or not, like whether they are statistically important or not, this is what the other columns would answer. We have the standard error, we have the t-statistic, p, confidence interval, all these, or all this part is about statistical significance. So I would need to go over each and every coefficient and find out whether, based on the null hypothesis that I'm going to show you, I'm going to discuss with you, whether these impacts are important, statistically significant, meaningful, or not. Okay? Do you have any question? Okay. When you watch my videos on the measures of fit, I wanted to connect it with this part of the table. Okay, if I might, like I don't think I have time to go over this today, but from today till we meet next week, I wanted to connect this part with my discussion on the measures of fit. Okay. All right, so let's move to the iPad. And on the iPad, what I'm going to show you, or what I'm going to discuss with you, is the statistical significance of the coefficients using T, P, and CI. And we are going to use this in order to determine whether what we see in terms of coefficients are statistically important or not. So let's go back to the iPad. Okay, and okay, so what I want to show you is an example related to statistical significance. And I think this won't be like something new for you. We have discussed statistical significance many times before. And we're just going to put it in the context of the OLS. So again, so our topic is about statistical significance. Statistical significance. I have a model, again, beta naught plus beta 1 x1i plus beta 2 x2i plus, okay, and suppose this is an estimated model. So we have the hats here, we don't have the error term. And now I have estimated these coefficients, assume that we got the numbers, but we want to know whether these are statistically significant or not. So we will need to have a null hypothesis and an alternative hypothesis for the test. Suppose that I'm going to test the impact of x1. I know that beta hat 1 is measuring the impact or the change in yi because of the change in x1i holding constant. So everything else is held constant, right? x2 and x3 and everything, xk. So each and every coefficient is measuring just the effect of the variable, the related variable, and holding constant all other variables. So my null hypothesis would be, let's think about this one. So I would like to test whether the expectation of beta hat 1 is equal to 0 or it's not. So in order to do that, so what I can see here is a two-sided test, right? I'm not sure whether X1 has a positive or negative impact on Y, so I'm just going to be on the safe side and have like a two-sided test. However, in many of the examples that we discussed today, I might have an idea about the direction of the relationship. It might be, if I'm talking about earnings and average earnings and age, I'm expecting a positive relationship, right? Earning and experience, I'm expecting as the person builds on experience or increases the years of experience, then the earning also would increase. But the default in Stata would be a two-sided test. You can always override the default, but the default would be a two-sided test. So this is for beta 1, but I can also write it in a general form and say, okay, my null hypothesis for each and every beta, let's call it beta j, is equal to 0. And my alternative is that my expectation of beta j, where j can be any number, 2k, right? It can be any number, it can be any x. How can I determine the statistical significance? So number one is I need, I have steps. So step one, I need to calculate the standard error of beta hat j. Number two, I need to calculate the t-statistic, which is equal to the beta hat j minus beta j under the null. I see the beta j under the null is 0, right? So what is my assumption of the beta under the null divided by the standard error of beta hat j? So this is the t-statistic, okay? And then step number 3 would be is to compute the p-value. And if I'm talking about a two-sided test, then it would be 2 times all the points that are less or equal to, so we're using the cumulative distribution function, CDF, right? So this one is the CDF, the cumulative distribution function. All the points that are less or equal to the absolute value of the t-statistic that we just computed, right? And we take an absolute value. And also you can also write it in a different way. So you can say it's 2, if you want to use the positive part. So it's going to be like 2, 1 minus the positive part, right? So 1 minus all the points that are less or equal to t actual. Okay. I prefer to use the negative ones, just easier. So this one, the first one would be like this. Give me all the probability of the shaded region right under negative t, and it's absolute, so it's a negative value. And this is just an alternative way of writing it. The one here refers to everything, right? Everything. This is the one I'm going to subtract from it. Anything that is less than the positive part. This one is the positive part, so this is t. What is, you didn't, okay, I think you need to ask me what is t actual. Let me go back here. I'm going to call this one t actual because this is the actual one that I computed, because I can have multiple t's. So this one is the t actual that I have computed. So you can call here actually t actual. Okay, so everything minus this part, then I'm left with, again, it's symmetric, right? So you're left with this. So you can either follow this way or this way, you will get the same number because it's symmetric distribution. Okay, so we have 3 steps in order to perform the statistical significance. We can actually also you can actually do the confidence interval. So let me add here the confidence interval also. As step 4, you can do the confidence interval. Okay, so what is a confidence interval? I'm going to take this beta j minus beta j under the null over the standard error of beta hat j, and I know that it's greater than a certain critical value and it's less than a certain critical value, right? And then we can say that this beta j, it lies in the interval that is equal to beta hat j minus the critical value, right, times the standard error of beta hat j, comma, beta j plus the critical value times the standard error of beta hat j. And the critical value would be like whatever significance level you want to use, whether it's a 5%. So as you know, like we have multiple critical values. So it all depends on your significance level and you can get a critical value. So if my significance level is 10%, 5 or 1%, then you can have your critical value, right? So this is, you can find it from, you can find it from your Z table. And so you can use, like when you go back here, if I'm using 5%, then I'm going to replace this one by 1.96, right? And this one by 1.96. So it depends. It depends on what significance level you want to use. So the good news is when you follow the 4 steps, you said step 1, you calculate the standard error. You're going to use it to go to step 2 because the t-statistic would depend on the standard error. And then actually you take it to compute step 3 because the p-value depends on the t-statistic. And then when you go to step 4, the confidence interval depends on the standard error again. So they are all connected. And that's why when it comes to the question whether the coefficient is statistically significant, you can choose either, like you have options, right? You can go with the t-statistic to determine the significance of the coefficients. You can use the p-value. You can use the confidence interval. This one would give you a certain number that needs to be compared with a critical value. This one would give you a certain percent that needs to be compared with significance level. This one would give you an interval, right? That you want to make sure that does not include the 0. So you have different ways. As long as the question doesn't ask you which one to choose, you can actually choose the one that you prefer. Okay, and of course the t-statistic is the easiest. Okay, so let me, the one thing I forgot to mention is the good news is I will give you the standard error most of the time. So the question would always include the standard error. So you don't have to worry about computing it, although computing it is not like hard to do, but just I want to let you know that this would be given to you in the question. Okay, so let's let me show you an example. All right, so suppose that I'm just trying to figure out which one. So suppose that I have a model like this. I have the test score as is equal to 686 minus 1.10 student per teacher ratio minus 0.65 the percent of English or the number of students still learning English learners. Okay, and then right under each coefficient we have the standard error. So this one is 8.7. This one is 0.43. This one is 0.031. Okay, so each one has its own standard error, so it's given in the question. So what we want to do, what we want to test is, we want to check whether student teacher ratio has a statistical significant impact on test score. So this is like our objective. So we want to check whether student-teacher ratio has a statistical significant impact. So I can see what I can see is just a number. We had analyzed number that for each additional student who enter this classroom or per teacher, the test score drops by 1.10 points. But whether this 1.10 points is statistically important or is just coming by chance, or if I repeat this experiment 100 times, will I be able to get around this number? And so on. So we need to kind of set up our null hypothesis and the alternative hypothesis. And the null hypothesis would be that beta hat 1, let's call this one, and so this is beta naught, this is beta 1, right? And this is beta 2. So whether beta 1, which is for student-teacher ratio, is equal to 0 or not. Right? Step 1, in step 1, I already know that the standard error is given, so you don't have to compute it. It's given as 0.43. Step 2, the t-statistic is equal to the coefficient minus the coefficient under the null over the standard error of the coefficient. And this would give you a number which is negative 2.54. Step 3, calculate the p-value. So the p-value would be 2 times all the points that are less or equal to negative, absolute, negative 2.54, which is equal to 1.1%. This is 1.1%. Okay, so 1.1. Right, 1.1%. So what we need to do now is to check or compare our results with the critical value and the significance level. I know that we need to make a decision, right? So to make the decision on the null, on the statistical significance of beta 1, I have two options, right? My first option is to compare the t actual versus the critical value. Both are not, right? Two need to be compared together. And I have another option is the p-value with significance level. And both of these are in percentages, right? This percent and percent, and this is just a number, and this is just a number. So the number that we have for the critical value needs to be determined based on what significance level you want to use. Suppose I'm using 5%, right? So this is my significance level. So this is the 5%. It's a two-sided test. So 2.5 under each tail. This is 2.5, 2.5. And the critical value here would be the 1.96, negative 1.96, right? So to compare this number, I have here, this is 1.96. And I have the absolute value of the t here is 2.54. It's bigger, right? What does that mean? So if I have here this one, and this is the 1.96, the 2.54 is somewhere here. It's in the rejection region. And this is also a rejection region, right? So my conclusion is reject the null. And if I reject the null, what is the null hypothesis? Let's go back here. This is the null. I'm rejecting the null, accepting the alternative. I'm rejecting the null, and this is very important because many students get confused with this point. So I'm rejecting the null that beta hat 1 is equal to 0, right? And accepting the alternative. So your conclusion is beta hat 1 is not equal to 0. In other words, it has a statistical significant impact on test score. So it's, you can say it's statistically significant. So beta hat 1 is statistically significant. So whenever you reject the null hypothesis, given that the null is that the impact of this coefficient is not different from 0, then you would accept the alternative that it's not equal to 0 or it has some effect. It could be positive, it could be negative, right? But you are rejecting the null, accepting the alternative, and the main conclusion is the effect is statistically significant. So this is following the t-statistic, but you would reach the same conclusion, the p-value, because the p-value we found it as 1.1%, which is less than 5%. Again, if I look at the graph, right? This is 2.5%. This is 2.5%. So you basically, because it's a two-sided test, you are dividing it between the two, right? And the 1.1%, you're dividing it between the two. So it's going to be like very small. Let's say here, 0.55%. And this one would be like very, very small, 0.55%. So you are again in the rejection region, right? Because as the p-value increases, you keep like getting closer to the 0, but you're actually here. So 0.55, or you can say like this, or 0.55% is less than 2.5 if you want to divide both by 2, like it's equivalent. And again, I reached the same conclusion. I'm in the rejection region. I'm going to reject the null and conclude that beta hat 1 or student-teacher ratio has a statistical significant impact on test score. Do you have any question? Okay. All right. Okay. So you can also reach the same conclusion from the computation of the confidence interval, right? So the confidence interval, I actually didn't compute it, but you can compute it and you will reach the same conclusion. Is so the confidence interval of beta 1 is equal to, so you get it from the coefficient minus the 1.96 times the standard error, and this is the lower limit, and you have the upper limit 1.10 plus 1.96, 0.43, and you close. This is the upper limit. Okay, so this is what we call lower limit, and this is what we call the upper limit. And if you compute this, you will find that no 0 in this interval. And if there is no 0 in this interval, I'm going back to the same conclusion because I'm actually checking whether there is a 0. And if there is no 0, then I'm again rejecting the null. So I didn't compute actually the numbers, but it would be, you will find that it's a positive interval. And when you find no 0, so again, reject the null. And if I reject the null, you actually compute that beta 1 is statistically significant. Or you can say that student-teacher ratio has a statistical significant impact on test score. So whatever the number that we found, which is 1.1, is not only a number, but it's a meaningful number. It's statistically important, statistically significant. Okay, what else? So it's basically like whatever I'm doing, it can be done with other, like each and every regressor that you have. So when I let's say show you this example. So suppose that we expand the model and we decided to include expand the model by including include the expenditure per student. So how much the state is paying as spending per student, whether it's for the desks, whether this is for the books, whether this is for computers, whatever. So we're talking again about the same model. We have 400 and something districts in California. We're trying to figure out the factors affecting the average test score per district. And suppose that we expanded the model to include an additional variable. So again, we're talking about multi-regression model. So the new intercept would be like student-teacher ratio plus 3.87, and this is expenditure ST, expenditure per student, and then minus 0.656, the same variable that we had from the previous slide, English learners. For each coefficient, we have its own standard error, 15.5, it's given. Okay. So when we had expanded the model, I want you to notice the following. So again, like this is very important. So every time I'm adding a new variable to a model that I already had, I need to check what happened to the coefficients that I already had in the model. So let's say here. So my model here used to be, this one was 1.10, right? This one is 0.65. What happened to these coefficients? Actually, this one stayed around the same number, right? Didn't change much. But this one had, right, has totally changed. It was 1.1. Now it's 0.29. So whenever I add an additional regressor to the model, I need to check what happened to previously included regressors. In terms of magnitude, like in terms of magnitude, it used to be, so student teacher ratio, or the beta of student teacher ratio used to be negative 1.1. Now it's 0.29. See, there is a big, there is a big drop, right? So you need to think, okay, it might have been the case that this impact was absorbed in here. It might be the case that these two variables are correlated with each other. So I need to make sure that I don't have a collinearity issue here, right? I'm not saying it's a violation of OLS assumption because OLS said perfect multilinearity. So I do not expect that these two variables are perfectly collinear, but it might be the case that they are imperfectly collinear. And that's why once I included this variable had dropped, right? It used to be negative 1.10, now it's negative 0.29 after adding the expenditure per student. This is only one thing. The other thing I need to check is, so this is about the magnitude. The other thing is about significance. Is it still statistically significant? So let's check. What about the t-statistic? So it is 0.29 minus the value under the null, which is always 0, over the new standard error. Now it's negative 0.60. Now the 0.60 is less than the critical value of 196. Now I can going to say it's not significant, right? It's not significant because now the value of this t-statistic is telling me that the impact of student-teacher ratio, which used to be statistically significant, it's not anymore statistically significant. So each and every time I'm adding a new variable, I need to actually be very careful of what happens to the originally included variables, especially when I'm 100% sure that student-teacher ratio has an important impact on test score, right? So in terms of magnitude, it had dropped, right? In terms of statistical significance, it's not anymore statistically significant. So I need to kind of pay attention to what happened. So t-statistic is not only about magnitude, it's also about the standard error. So let's go back and check what happened to the standard error. The standard error used to be 0.43. Now it's 0.48. So it had increased, right? But it's actually the highest impact is coming from the numerator, which is the magnitude itself. So dividing this by this, making the coefficient no more statistically significant. So this is one of the things that we will talk about next week, which is how the inclusion of variables would affect the already included variables and whether I actually need to have this problematic variable into my model. Is it actually needed or it's not needed? How can I perform a test to see whether it's needed or not? So this would be what we will discuss next. The last thing I want to show you is how can I check the statistical significance on Stata. So I'm going to go back to my do file. So I'm going to share with you the desktop. And this is gonna be the same model. So it's kind of easy. It's not like you're not going to compute something. In the output, this is the coefficients. These are the standard errors that you have in the brackets right under the coefficients, so you actually don't need to compute them. If you divide this by this, you get the t-statistic. You divide this by this, you get the t-statistic, because this one is actually subtracted from the 0, where the 0 is your default. Okay, so the t-statistics are already computed here in this column. All what you need to do to determine whether age has a statistical significant impact on AHE is to see whether this one exceeds the 196, because we are using a 5% significance level here. So you can actually, if you want to use the 10%, then just compare this with the 1.64, right? Because if I'm using one-sided, two-sided test, t-statistic is the same here. It's not going to be different. So all what you need to check with is actually the critical value. So if I'm using the 5%, it exceeds actually all of them, or 1, 2, 3, they exceed the 1.64, the 196, the 2.59. So based on the t-statistics here, I can say that age has a statistical significant impact on AHE, and the same thing for bachelor, and the same thing for female. Each one of the 3 variables have a statistical significant impact on the average hourly earning. the constant of the regression is not actually statistically significant. It's falling below the 1.64, which is the critical value under the 10%. Okay. Looking at the p-value. So Dan is asking me, why do we check the t with the standard error? We're not checking the t with the standard error. I'm saying with the critical value. Okay. So let's say the 12.91, I'm checking it, or I'm comparing it with the critical value, which is 196. This number is bigger than 196. So I'm going to say that we are in the rejection region. So you reject the null hypothesis and you accept the alternative that age has a statistical significant impact. What I said about the standard error is that I'm using it to compute the t. So I'm getting this coefficient divided by this number, I'm getting this number. Is that clear? Okay, good. In terms of the p-value, it's actually computed the same way that I showed you on the iPad. So what you need to do is just use the cumulative distribution table. You multiply times 2 times the critical 2 times the CDF of this number. It's already positive, okay? And you get the p-value, so you can actually try and you can actually replicate all the numbers that you see. Again, this one is computed the same way that I showed you on the iPad. So, but remember, this one is using the 95 confidence interval, so it's using the 1.96 critical value. All right. Okay, so I think it's kind of relatively straightforward. What I want you to do is, okay, so, okay, what I want you to do is, let me just go to Sakai. I want you to go over the content of course, if you haven't watched these videos in week 8, then go ahead and watch them. These videos would complement what I discussed today, okay? And then week 11, which is today, I want you to watch the regress command. Again, it's repeating what I just said in case you missed anything. So this is about the regress command. And then you have an example here using the teaching ratings data set. So you can watch these 2 videos and it would make like your life easy. It would, you would be able to figure out how to estimate the models using Stata easily. I will leave this for next week. So I will move this to week 12. I just want to make sure that you are absorbing the materials before I test you on it. So, and I know it's relatively challenging, so I'm going to move this to next week. Okay. Do you have any questions? Okay, great. So I'm going to this, perfect, okay. So this lecture is recorded and I'm going to post it under week 11 tab in like in an hour or so. So you, in case you missed anything, you can just play it again and take notes, and you can, if you have any question, you can just email me or post on the discussion forum. All right, so I'll see you again on Wednesday, and again we're going to do the same thing. I'm going to be sending you the Zoom invitation. It's going to be recorded, and before I see you on Wednesday, I just want you to go over all the videos on this week and on week 8. All right. Okay, stay safe and stay well and healthy, and I'll meet you again on Wednesday next week. All right.